Pitch blade turbine impeller design and modeling for agitation in baffle and unbaffled standard tanks. We are Group 3 from the Department of Chemical Engineering from Los Andes University. The index for the presentation is Objective, Introduction, Standard Tank and Pitch Blade Turbine Impeller Geometry, Mesh Generation, Physical Model Specification, Results and Discussion, Conclusion, and References. The objective of the project is determine the effect of implementing baffles to a stirred tank with a pitch blade impeller on the flow patterns, power, pumping, and general performance of a stirred system. Agitation and mixing are truly important unit operations in a wide variety of industries. Typically, these operations are related to the processes that require physical and chemical reactions, food, pharmaceutical, and even oil and gas industry. Even though agitation and mixing units operations are strongly related, they are not the same. Mixing, any operation used to change a non-uniform system into a uniform one. Agitation implies forcing a fluid by mechanical means to flow in a circularity or other pattern inside a vessel. This project focuses on agitation, suspension of solid particles, dispersion of a gas through a liquid in the form of small bubbles, promotion of heat transfer between the liquid and heating coil or a jacket, and many others. There are several agitation units in the industry, but probably the stirred tanks are the most known. Probably the most important part of the stirred tank is the impeller, because it changes according to the desired property of the mix or the purpose of the process. It also determines the type of flow, the efficiency, the power consumption, and so on. In this project, a pitch blade turbine impeller is studied, located on the right section on your screen. The main characteristics of this impeller are mixed flow impeller, both axial and radial due to the form. Typically used at high Reynolds and low viscosity, but it can work in laminar or turbulent regime. Useful for blending, dispersion, and solid suspension. It is especially used to homogenize and improve heat transfer. Generates strong currents which spread throughout the tank and destroy masses of stagnant liquid. Near the impeller there is a zone of fast currents, high turbulence, and intense shear stress. Now let's move on to geometry model and mesh generation. We had developed the geometry for the project keeping into account that we were going to be using a standard tank. The most special attribute of this type of tank is that the height is equal to the diameter. The height is 28.5 inches as well as the diameter. For the tank with baffles, we designed it so it has 4 internal baffles with 5.7 inches of width and depth, and the height is the same as the tank. The impeller that we designed was the pitch blade turbine P4. It consists of 4 blades equally spaced from one another that are inclined 45 degrees from the bottom axis. The measurements can be seen in the blueprint of the impeller. The diameter is 9.5 inches, the total height is 19 inches, the length of the blades is 4.21 inches.
An internal volume extraction and slice were performed in order to divide the static and rotation sections with an interface. Sections of the geometry and interface were named. The slip condition was specified at the top face of the tank and top of the solid of revolution or impeller axis section. A mesh was generated taking into consideration the highest Reynolds value and impeller width and diameter. Initial and reference conditions such as pressure and gravity were defined. MRF was specified for steady and RBM for unsteady simulations, calculating time step and maximum physical time. Simulations were carried out at various Reynolds values. Velocity scenes and worldwide plus scenes were generated, as well as other reports like mass flow rate, which depend on the mixed flow impeller behavior, pumping and power numbers, shear stress, between other reports. After this, flow behavior between simulations was compared. The mesh independency test was carried out through the variation of the base size, using the highest Reynolds value to determine the prism layer thickness and relative minimum size. 3 meshes were generated: coarse, reference, and fine mesh. It can be seen that while number of cells increased, CPU cost increased as well. Error percentage was similar, although as a higher number of cells generated higher accuracy, and to meet the 1.5 million cell specification, the reference mesh was selected. Polyhedral meshing model was selected as it has substantial amount of information of neighboring cells, which means a higher accuracy. Also, prism layer mesh as it has zones near to the wall where the no slip condition becomes valid. Physical mode selected in the simulation were K omega, as it has better performance, and its best advantage is that it may be applied throughout the boundary layer, generating more accurate results for the transition region as well as turbulent region. Turbulent suppression was also selected as it mimics transition behavior. All Y plus wall treatment was selected, which offers most mesh flexibility with good results on fine meshes for Y plus values below 1. So quality remediation lessens the impact of poor cell quality on the accuracy of the solution. Gravity, as it is important to consider its effect. Segregated flow, as it resolves flow equations in a segregated manner, saves CPU cost, and is used in incompressible fluids. SST Mentor Omega was selected, and it has the near wall performance and benefits of standard K omega without the sensitivity to free stream conditions.
Results and discussion. As can be seen in the figure, lower values of Reynolds generate lower values of Y+. It can be observed a proportional relation between these two values. It is recommended to use lower values of Reynolds so the value of the Y+ do not affect the calculations of wall shear stress. Additionally, it is desired that values around 1 are used so wall functions are more precise.
As shown in the table, the Kappa Omega model gave different performances for the baffle and non-baffle system. For the case of the baffle tank, a good agreement is observable at large Reynolds, while an overestimation was encountered at low Reynolds where early turbulent conditions are present. This appears somehow in contradiction with the model features, which is commonly considered as a turbulence model able to deal with low Reynolds cases where turbulence is not fully developed yet. For the case of a baffle tank, the model is somehow able to follow the qualitative trend report. More precisely, the model is capable of predicting the increasing of NQ up to achievement of an asymptotic value, although the latter is slightly higher than the literature one. As it concerns the unbaffled tank, a decreasing trend is predicted by the CFD simulations, unless for the Reynolds equal to 100,000. The higher Reynolds, the lower the slope of the points, thus indicating the achievement of some asymptotic value, which seems really similar to a one report. Based on the results obtained and correlations found, an equation for both baffled and unbaffled standard tanks was developed. Our results show that from Reynolds values from 1,000 to 100,000 NP values were near constant, as it was shown in literature. Therefore, our equation for NP based on our results for baffled tank is NP equal to 1.16, an average of the values obtained in CFD simulations. For our unbaffled questions, an equation for Reynolds was determined, although for Reynolds value of 100,000, it presents some deviation. For lower values like Reynolds equal to 100, high errors values were obtained, therefore not included in the development of this equation. The higher flow rate discharged by the impeller, higher NQ, should be somehow paid by higher power requirements, higher NP, in the baffled tanks at any Reynolds larger than the bifurcation one. Thus, the flow patterns occurring between so-called transitional regime conditions should be regarded as the main responsible for the differentiation of the two systems. Note that although the NQ versus Reynolds curve from literature has a different behavior from the one obtained by CFD simulation, the values are so close. When the axis is vertical and located in the center of the vessel, the tangential component of velocity is generally detrimental to the mix. Flows follows a circular path around the axis, which generates a vortex of the surface of the liquid that, due to the circulation in the laminar flow, gives rise to permanent stratification at different levels of unmixed substances. If solid particles are present in fluid, circulatory currents offer to throw these particles against the wall of the pond due to centrifugal force, from when they fall accumulating in the central part of the pond bottom. Therefore, instead of mixing, the opposite action takes place, that is concentration. In a pond without baffled plates, the circulatory flow will predominate regardless of the type of impeller used, whether the flow is axial or radial. At high rotational speeds, the ebb of the vortex can be so great as it reaches the blades, causing the gas above it to enter the liquid, which should be normally avoided.
RMS, it can be perceived that for higher Reynolds values, the difference between the pumping number values for lower Reynolds in the transition region represented high discrepancies and deviations from those values reported in literature for both baffled and unbaffled standard tanks. RMS values range and varied for the baffled tank about 15% and for the unbaffled tank about 35% for values of Reynolds between 1,000 and 100,000.
Reducing vortex formation may also be achieved by placing an impeller in an off-center position. This creates an unbalanced flow pattern, reducing or eliminating the swirl and thereby increasing or maximizing the power consumption. The exact position is critical, since too far or too little of center in one direction or other will cause grating swirling, errating vortexing, and dangerously high shaft stresses. Usually, 4 baffles are used and the clearance between the baffles and the wall is about 0.1 to 0.15 the baffle's width. This ensures that the liquid does not form stagnant pockets between the baffle and the wall. Baffles set away from the tank wall create turbulence and thus enhance the entrainment of liquid in contact with the tank wall. Another alternative is by adding another impeller in the axis, so it would mitigate the dead zones by increasing the movement of the fluid till the top of the vessel. If a fluid with a higher viscosity is mixed, it is expected that it requires a greater amount of power since it is necessary to find more force to be able to cut the fluid. The flow would follow the same behavior patterns as the water in the impeller and there will be more dead zones in the upper zone of the tank.
Conclusions. While Y plus increases as Reynolds values increases in the impeller, it was concluded that in order to improve the impeller and agitation tank's efficiency, a curved bottom could be implemented to decrease dead zone regions, as well as locate the impeller at a higher location in the tank or increase the number of impellers. This to increase agitation and homogenization of what is being mixed. Also, higher Reynolds values indicate higher shear stress as a greater force will be needed because the flow becomes more turbulent, which means higher power and power density. A higher viscosity in a fluid will indicate higher power values as the agitator or impeller will need much more force and probably more dead zones could appear.